Hello everyone. Now we have our regular webinar and Solver colloquium. Today we have talk by the Solver Drive Center Director, Jim Drake. Jim received his PhD degree from UCLA in 1975. Then he spent a couple of years as a postdoc there and then came to Maryland in a research position and then moved into a position of the teaching faculty. After many impressive accomplishments, he is now a distinguished university professor and the director of the Joint Space Science Institute, as well as the PI of the Solver project. Jim is a fellow of APS and AGU and the winner of the 2010 James Clerk Maxwell Prize in Plasma Physics and APS Award. So now Jim has a talk, electron acceleration during magnetic reconnection in macroscale system. So Jim, please go ahead and I will tell you 5 minutes before the end of your time.
Okay, so I'm trying to remember, are you giving me 50 minutes? Is that
45 minutes and
okay.
Yeah.
Okay, so yeah, I want to talk about our efforts to understand electron acceleration in flares, and in particular trying to understand how that acceleration takes place in macro systems so that we can directly try to model what's going on in real flares. And I just want to thank our co-authors on a recent paper on this and all of the Solver team. We've had a lot of great discussion over 9 months or even more now, and I've learned a tremendous amount, and I hope there others of you have also. In particular, thanks to Harry Arnold, a graduate student in Maryland, who's along with Mark Swistak, has played the lead role in developing a new computational model to be able to model real flares. Okay, so I'm going to start off with sort of an overview and some of the basics of magnetic reconnection, and then I'm going to talk about some experimental observations that have sort of steered us the way we've gone in trying to understand this. So first, just a very general statement about magnetic energy dissipation in the universe. Magnetic reconnection is the dominant mechanism for dissipating this energy, and the conversion of magnetic energy into heat and high-speed flows underlies many important phenomena in nature. Known systems are characterized by slow buildup and fast release. And importantly, and it's been well documented in solar flares, is a significant fraction of the released energy goes into energetic particles. And basically, the heliosphere is acting as a local laboratory to understand reconnection, a process which is important in many places of astrophysics. Okay, so I'm going to start off with the very basics. And so you can imagine that you have magnetic field lines that are, say, pointing in opposite directions. And the reconnection process is driven by the magnetic tension in newly reconnected field lines. So what you need to imagine here is by some magic, you break a field line here and a field line there, you cross-connect them, and you get this reconnected field line. And the plasma requires some dissipation to do that, but I'm not going to spend a lot of detail discussing that. The main point is that once you have this reconnected field line here and here, magnetic fields have tension forces, and that tension forces drives an outflow to the right and an outflow to the left at the Alfvén speed. That produces a pressure drop in the middle. That pressure drop in the middle brings in field lines above and below. They reconnect, and so the whole thing is a self-driven process. You can also add an out-of-plane magnetic field, which I haven't drawn in this picture, but it doesn't drive reconnection, but it also doesn't change the dynamics that much, at least as far as the reconnection process. As you're going to see, guide field does strongly impact the particle acceleration. So here's a classic cartoon of solar flare reconnection. You have magnetic fields going up here and then down. And there's a lot of motion in the chromosphere and photosphere, which twists these field lines around. And eventually you start getting reconnection going on, as illustrated here. Inflow from the two sides, outflow down, outflow above. You form a flux rope, which gets often ejected out. And then, of course, this represents the out-of-plane so-called guide field that can string through this whole system. So this is this classic simple picture of solar flare reconnection. So first thing I want to do is talk about timescales. We have to be able to explain these. This is from July 23rd, 2002, X-class flare. This shows hard X-ray and radio. Hard X-ray and radio. This is the radio. Here's the X-ray. And you see onsets in tens of seconds, and then durations here, hundreds of seconds. So that's the characteristic time scale. One must be able to understand energetic particle production in tens of seconds. And then from RESI spacecraft, the hard X-ray spectra, this is very typical, although this is a very hard spectrum from this event here. It's a gamma ray flare. You typically see a hot thermal component and a power law tail. So this is known as the hot thermals, and this is, of course, the non-thermal particles. And this is a photon spectrum, and then oftentimes you see a split power law in the particle spectrum. Okay, just to convince you that, in fact, that previous slide didn't really extend to very high energy, here's another one from Vilmer, 2012, showing the full extent of the photon spectrum up to around 100 MeV. So if you look at this, the electrons, this shows a continuum transition from hard X-rays to the gamma ray spectrum. And the spectrum of photons then extends from 10 kilovolts up to tens of MeV. So this is more than three decades in energy, which is a huge range of energetic particles in this flare. The other thing is that the emission or the photon spectrum from these things is not always very smooth. It can reveal lots of hard X-ray spikes. This has been diagnosed in lots of flares. These spikes can range from 0.2 to 2 seconds. There's a bunch of different papers which have explored these issues. And so one question is, well, why do you see these spikes? Is it, for example, because the reconnection process is bursty with lots of flux ropes and these spikes are then the merger of flux ropes? We don't really know the answer to that yet. It's often difficult to directly visualize with remote sensing where the flare energy is actually being released, and that's because the hard X-ray spectra from the foot points often dominates and then blinds the imager. Here is an example of an occulted flare, however, in which the foot points were beyond the limit of the sun, and that allowed the Crocker et al. Paper and the follow-up Oka paper to explore the details of the energetic particles up high in the corona. And the surprising conclusion from all that was that a large fraction of the electrons in the flaring region are part of the energetic component, ranging from 10 kilovolts to several MeV. And remarkably, the pressure of the energetic electrons approaches that of the magnetic field. In other words, any process you're looking at to understand energetic electrons and flares, that process must accelerate a large fraction of the electrons. And then here's another important set of results, and this has to do with the energy partition between thermals and non-thermals. Here's a plot from the Varmuth paper, 2016, vertical is the thermal energy content, and then the non-thermal below, and you can see the observational data falls below the straight line in which the contributions are equal. That's especially true in the strongest flares that have been observed. However, the NuSTAR data, which does a better job at exploring what happens at low energies, indicates that it's quite possible that even small flares, in small flares, the non-thermal electrons actually dominate the energy content. So first thing, I'm just going to say something very brief about the rate of magnetic reconnection and energy dissipation. It's not the main focus of this talk, but I do want to say something. So there's basically been two mechanisms identified for fast energy release. One is the so-called Hall reconnection, in which basically there's an open Pechek-like outflow, and you can see so reconnections occurring in this narrow region. Then you have an open outflow geometry, which produces fast reconnection at around 1/10 of the Alfvén speed. The inflow velocity is around 1/10 of the Alfvén speed. And then there's a second possibility for fast reconnection, and that typically happens if you look at low resistivity MHD models, that sort of thing. In that case, you get these long current layers, but they break up into many, many magnetic islands. These magnetic islands allow the plasma flux to escape, and the consequence is also relatively fast reconnection. And both of these, either one of these is sufficient to explain the fast energy release in flares. It's much faster than the old Sweet-Parker type of model. Okay, so I'm going to talk about particle acceleration now. And first statement is that, so here's a typical single reconnection exhaust into an island. And the crux is that the change in topology during reconnection, which is occurring in this very small region here, is not where the energy is really released. Remember from the picture I drew at the beginning, there is a bent field line here, and as that expands out, it is what is releasing the magnetic energy. So the dissipation region proper, which is this very small region, is not where the energy is released. It's released in this outflow region here. And that means that any mechanism you're looking at, you really need to explore mechanisms that can take place in a much larger domain. Okay, so here's the basic mechanisms for electron energy gain, and I'm writing down this equation valid in the guiding center limit because that's really the easiest limit to try to understand. So rate of energy change of particles, actually it could be even electrons or ions, doesn't really matter. You've got the parallel electric field term multiplied by V parallel. You have the curvature drift term dotted into E. And you may not be that familiar with the curvature drift, but the physics of this is really simple. This is the slingshot term. You can understand it by just looking at this diagram here. You've got a bent field line, which is expanding out at the Alfvén speed. If you have a particle coming in here at V0, goes slinging around here, and it comes out at V0 plus twice the Alfvén speed. This is so-called Fermi reflection. This increases the parallel energy of the particle, and it arises from the curvature drift dotted into the electric field.
I'm going to be focusing on our sort of alternate theory that is firmly rooted in the first principles of Coulomb and volume.
Okay.
Jim, please go ahead.
Okay. And then so there's the E parallel, there's the curvature drift, and there's grad B drift. And the grad B drift is associated with mu conservation. Mu is V perp squared over B. This is a conserved quantity in the guiding center limit. However, this is not really playing a dominant role in reconnection. Typically, the magnetic field strength goes down, and that means V perp squared goes down, and so this is actually an energy sink. Okay, so the question is, what about if you're looking at reconnection, then which of these three mechanisms plays the important role? And this was explored in PIC simulations, and I just want to have a very brief slide on PIC. Probably most of you know this very well, but just a reminder for those just getting into the field. So what is a PIC simulation, particle and cell? Basically, you throw a bunch of particles on a grid. It can be electrons and protons or electrons and positrons. You advance the particle motion in electric and magnetic fields, calculate the currents from the particles, advance E and B using Maxwell's equations, and then you go back and just keep repeating the cycle over and over again. That's the PIC model. But we do need to recognize the constraints of PIC, and that is, in PIC, you have to resolve key kinetic scales. In particular, the challenging one is really the Debye length, although the electron skin depth is also a challenge. And the Debye length is of order 1/10 of a centimeter for the corona. So this is insanely small, and characteristic flare sizes are maybe 10 to the 4th kilometers. And so this ratio is enormous, and that is a significant problem for PIC simulations that are really trying to understand what's going on in flares. And the bottom line, of course, is that PIC's models can only explore extremely small domains compared to the real system. Okay, so there's been a number of papers in the last 5-6 years on exploring which of these three mechanisms I mentioned before are responsible for electron energy gain. So I'm going to show you one from Joel Dahlin in 2014, 2017. Large PIC simulation. Starts off with a thin current sheet and many, many islands forming and merging. So the merger process is important, and this simulation explored all that. And what Dr. Dahlin did was then evaluate how electrons are gaining energy during this entire simulation, adding up and exploring all the particles in the domain. And here's what he found as a function of time. He looked at the Fermi reflection, which is red. The total energy gain, by the way, is in black, and E parallel is in green. And then the mu conservation is the blue term. So you can see the blue terms are negative. It's a sink. The real surprise in this simulation was the dominance of Fermi. Here's the paraelectric field. It's small, so Fermi completely dominates 4 small guide fields. This is a small guide field.
Jim, could you clarify what exactly is plotted along y-axis?
This is the rate of energy gain of electrons. So this is a rate of energy gain. Sorry about that, I should have plotted that. So this is the rate of energy gain. So it's bursty. You can see the electrons are gaining energy in a bursty way. And this is because of the merger of various islands in the system. So you might ask about whether these bursts have anything to do with the bursts of X-rays, and we don't know the answer to that yet. Okay, in any case, as you crank up the guide field, the paraelectric field actually becomes comparable to the Fermi terms. And so that establishes E parallel and Fermi as dominant contributions. And that's shown here. Here's the total energy gain of electrons in a simulation versus the guide field. BG is the guide field, BR is the reconnecting field. And you can see the Fermi term is dominant at low guide fields and then drops off at high guide fields. E parallel is small at low guide fields and dominant at high guide fields. So remember this, what's going on here is the Fermi term goes away at high guide field because the effective radius of curvature of reconnected field lines is strongly increased by the guide field. Okay, so E parallel dominates at large guide field, Fermi at small guide field. So why is that important? Let me go to this slide first. That's important because if you look at the production of the most energetic electrons in the simulation versus the guide field, you can see that at low guide fields, you get a lot of energetic electrons. At high guide fields, you get almost none. And what that means is that since Fermi is dominating at low guide fields, it's the dominant driver of the energetic electrons. E parallel produces almost no energetic electrons. And I just want to emphasize that point again over here. Here's for a modest guide field, how particles gain energy versus their energy. And you can see that when the particles don't have much energy, they gain it from E parallel. Once they have a lot of energy, they get it from Fermi. And the reason is simple. You can see this equation here. The rate of energy gain is proportional to first power in velocity for the E parallel term, and the curvature drift is quadratic. So high energy particles gain energy from the curvature drift. And that's even more clearly seen here from Lee et al. 2019. And you can see as a function of energy, again, this is the rate at which particles are gaining energy. And the E parallel actually is a sink for the energetic particles. Okay, so what does that all mean? It means that we always thought that E parallel was the driver of energetic particles, and it does not seem to hold up from all the PIC simulations that have been done. Okay, so what I want to do now is talk about how you start getting up to MeV electrons, relativistic electrons, and flares. So first of all, just imagine you have a single X-line situation, and there's been a lot of exploration of single X-line dynamics, both in the laboratory and in the magnetosphere observations. And the conclusion from all that is that the energy gain of electrons is proportional to the available magnetic energy per particle, and that's simply given by MICA squared. This is the available energy per particle. And the electrons in particular get a relatively small fraction of this, but in any case, this is an upper limit on how much energy the particles can gain in a single reconnection exhaust. And this may be for a single X-line reconnection. In flares, it's at several keV. So single X-line produces several keV electrons. It's simply not sufficient to produce very energetic non-thermal particles in flares. And the bottom line from all this work here is that slow shocks, which have been invoked, do not seem to be very effective in producing non-thermal electrons in flares. Okay, so single X lines are not sufficient. People have started then to explore if you have multi-island type reconnection, so you have interaction of particles with many islands. And there's been a lot of past papers way back to Tajima and Shibata who've been proposing this. And so I want to explain to you then how it is that multi-island reconnection can quickly boost electrons up into the relativistic regime. Okay, and so I have a simple example, and that is we just consider the merging of two round islands and ask how much energy gain do the electrons get during this merging process. And it's an easy problem to do. Basically, to lowest order the area and magnetic flux, namely the flux going from here to here, for example, is a preserved quantity. These two want to merge and, of course, form a single island, round island, but the flux integrated here is the same as the flux there, and the area, the sum of the areas is about the sum of the area there. And then you can use conservation of magnetic moment, and importantly, the conservation of the parallel action. So if you look at the length of a field line like this, of two lines that are just starting to reconnect, then as you go from here to here, that field line shortens. And it's the shortening that gives you the energy gain. So the line length goes down, that means V parallel goes up. If you look at the merger of two equal size islands, the length of the field line goes down by square root of 2. That means V parallel goes up by the square root of 2. The particle energy doubles. Okay, so a single merging of two islands basically doubles the energy of all the particles inside. Now, it turns out if you add a guide field to that, it really starts inhibiting this energy gain. And the reason is, if you look at the length of the field line with a guide field, then you have to take into account the length along the guide field direction as well as the perpendicular direction. And you can see that if you go from a length like this and you reduce the reconnected field line from here to here, you only get a small change in the field line length. So the guide field basically strongly inhibits line shortening and energy gain. Okay, so let me show you how you get MEV electrons in the corona. And so the argument is that it's a two-step process. Here it is. If you have a single X-line reconnection, you get several keV. And so for 50 Gauss, n equals 5 × 10⁹, then you get, if you put a quarter of that energy into electrons, you get about 2 kilovolts. So a single X-line gives you a couple of kilovolts, and now you want to go up to MEV. Okay, well then you can look at island mergers. Each merger doubles the energy due to field line shortening. How many mergers do you need? Well, 2 kilovolts times 2 to the n has to be 1 MeV. You get n equals 9. You need 9 mergers. Okay, so is that fast enough? Well, let's take a typical island size of about 10 to the 2 kilometers. Merging time is about half the width of that, divided by 0.1 times the Alfvén speed, using these numbers up here, 0.4 seconds. Interesting that merger time is about the same time as the hard X-ray spikes seen in the data. And then if you want 9 mergers times 0.4, that gives you about 4 seconds. So you get 1 MeV electrons in about 4 seconds. That's about consistent with what's seen in that rise time for that flare I showed you at the beginning. So all you need is about 9 mergers of islands to pump electrons up to an MeV. Okay, so let's start talking about simulations and their ability to reproduce the power laws seen in the observations. Honestly, it's been a really big challenge to get power laws. For many years, we've been trying to work on that, and it's only been in the last year or two when some of the biggest PIC simulations carried out have actually been successful. Here's one from, again, that same Lee et al. 2019 paper. This was a truly massive simulation. And here is the particle spectrum as a function of energy. And there is a power law. There it is. And of course, we all celebrate this because it took us so many years to finally get one of these things. But, you know, in many ways, it's disappointing because it only goes about 1 decade in energy. And this is a horrendous simulation. But so the question I think one must ask is why aren't why aren't the PIC simulations giving us more extended power laws? And well, this is still an ongoing debate as to what the problem is. But I think the problem, I suspect, is that there's really an insufficient separation of scale between the Lama radius of energetic electrons and as they're produced and the island structures seen in the simulations. And the problem, of course, is if the energetic electrons have Lama radii which become the same size as the island structures, then you're in trouble. The electrons demagnetize and you don't get coherent acceleration like we expect to see. Okay, so how do we get around this problem of PIC simulations and their limited scales? So we've tried to put together a model which brings together a particle description and an MHD description. And keep losing my mouse, here it is. In an attempt to try to model electron acceleration in macrosystems. And basically, the way we do this is we simply order out all kinetic boundary layer scales in the equation. So there is no more kinetic scales. And the reason that makes sense is because it's Fermi reflection that dominates the production of energetic electrons. And Fermi reflection does not require kinetic scale boundary layers. It requires the dynamics of many magnetic islands interacting with each other. So it's not boundary layer physics. It's macro scale physics of macro scale islands. So the way this model works is we have electron particles distributed on an MHD grid. They revolve with the relativistic guiding center equations. So we don't have to worry about demagnetization. And importantly, what you get out of that is an electron gyrotropic pressure tensor, and that feeds back on the MHD fluid. This is critical because if you get a lot of pressure into the energetic component, that feeds back by bumping against the marginal fire hose condition, which suppresses magnetic tension and suppresses the reconnection drive. So feedback is critical, and it's included in this K-global model. We facilitate reconnection with a hyperresistivity. Regular resistivity tends to be overly diffusive, so we use a hyperresistivity, and you can write down an effective Lundquist number, which is the viscous diffusion time over the Alfvén time. It's given by this. And this is a measure of the size of our system. Just like in MHD, the Lundquist number is a measure of the size of the system. In our case, it's the this hyperviscous type Lundquist number. So let's now look at what we get. And so here's a movie. It's got 3 panels in it. Each a panel, there will be a current sheet in the middle. You can see it here on this one. The top one is the electron energy. The second one is the fire hose parameter. So this tells you whether you're going to suppress the tension and field lines, and then the bottom one is the current. And so here we go. So you see we form many, many small islands, and they go through many mergers, producing more and more energetic electrons. So here they are. The most energetic electrons have been ejected out into these large islands, which form at the end. You can see here's the current distribution. You can see merging current sheets developing, all that sort of thing. And here's the fire hose parameter. Blue is at fire hose unstable. White is basically marginally stable to fire hose. These islands are completely dead. They're at the fire hose condition, meaning that they have no more magnetic tension. So these are dead islands. No more particle acceleration within these islands. Okay, so what kind of particles do we get out of this? And so here's the electron power law spectra from K-global. And so here we are log plot. And here is from a simulation with a weak guide field of 0.25 of the reconnecting field, showing the time development. Here's the initial state, cranking up in time. At late time, you get a power law distribution, and this extends nearly 3 decades in energy. So honestly, we are totally amazed. This just popped out automatically. We didn't do anything special with this code. It just produced these energetic electrons spectrum. If you ask how that spectrum behaves as you go to larger and larger systems, remember this effective Lundquist number measures the system size. So here we see spectra in several different system sizes. The green is the biggest. That spectrum goes off the end here. And so, but the slope is not that sensitive to the system size. If you look at the particle dynamics that are producing these spectra, it's Fermi reflection. You can see that here. Here's energy gain versus position. Particle is trapped in an island. It's undergoing Fermi reflection and just goes shooting up in energy. This is what drives the energy gain in these simulations. This little plot here shows you what happens when you start cranking up a guide field. So here is the weak guide field, and then going to strong guide field. You can see the guide field really turns this thing into a very soft spectrum. So the guide field is crucial to understanding the power law spectra of the energetic particles. So what Harry has been able to...
Can I just interrupt real quick and ask you about the... you said that those flatter slopes are not that much different, but it looks like it's going to like delta 2 or so.
Okay, so I don't think I have a plot, but if you compare it with the impact of the guide field, so maybe that's the context for this statement.
Right.
The guide field really very strongly impacts the slope. I don't think I don't have a plot here to show you how this varies from here to here, but I can certainly produce that, and then we can let you know what the answer is. But the guide field has a much bigger effect. You can see that here. It certainly is a control parameter. There is some dependence here. So I agree with what you said. Okay, so a very important thing is the partition between thermal and non-thermal. So what Harry did was he looked inside the late time islands and analyzed those by representing them by a kappa distribution added to a Maxwellian. And if you then do the fitting with that, you can immediately then calculate the amount of energy and the number density of the Maxwellian particles versus those in the kappa distribution in the power law part of the kappa distribution. The kappa distribution, of course, has a Maxwellian built into it, but the non-thermals then are in the power law portion of the kappa distribution. That allows you to calculate the numbers and the energy density of the thermal and non-thermal particles. Okay, so this is what you get as a function of guide field. This is the fraction, the percent of energy density in the non-thermals. And you can see it's up here to about 80%.
So Jim, this is in fact fraction, not percent.
Oh yes, fraction. Sorry about that. Well, that's a good thing. You didn't catch that in the reading of the paper. This is the fraction.
I did, in fact, but it's not relevant now.
Yes, right. This is the fraction. So 0.8. So the non-thermals have 0.8 of the total energy in the electrons, and their number density is about 0.2 to 0.3 for weak guide fields. And you can see what happens at large guide fields. There's almost no energetic non-thermal electrons, and their energy content goes way down to a very small fraction. This means we really need to figure out what the guide field is in flares. One way or another, we have to figure this out if you believe at all what we're talking about here.
I have a comment if you'd like to hear it.
Luke, we'll wait, because let me finish first, and then you can make a comment, okay?
Right.
Okay, here is the energy content versus the guide field, the total, and in the thermal component. So now we're talking about hot thermal. Hot thermal is relatively insensitive to the guide field. We don't understand this. We're trying to explore what it is that's doing the background heating. So it's really not known now. Okay, let me comment about the power law indices. So here's the power law index of the particle spectrum, not photon spectrum. This is the particle spectrum as a function of guide field. The stars are from the simulation. You can see that it becomes a very soft spectrum if you go to large.
Jim, you have 5 more minutes.
Okay, yeah, I'm doing fine. And then we also have an analytic model that we've developed that you have basically island merging in a current sheet of some length and then convective loss. And you can analytically calculate the spectrum, and this is what it looks like. Spectral index, I'm sorry. The spectrum goes like a power law, W to the minus delta. This is the power law index for that model. And if you can lay it on the same thing, it's the red curve. The best match is for a characteristic island size over the length about 0.22, which is really what's pretty much seen in the simulation. So this model seems to explain the dependence on the power law. Okay, the last thing I want to talk about is we've made a rather large effort to try to compare the modeling effort with the September 10, 2017 flare. So a reminder, this was a limb flare. It was seen by a lot of spacecraft and ground-based instruments. And the beautiful thing was having RESI and EOFSA together at the same time. The AIA reveals a classic erupting flux rope. Here you can see it here, and then in the vertical direction, here it is from the AIA. The MHD simulations are overlaid, I think, on the last plot down here. They agree nicely, actually, with what seems to be the flux rope structure. RESI shows soft X-rays down here with hard X-rays above the soft X-ray loop. And EOFSA reveals a broad spread of gyrosynchrotron emission going from high magnetic fields down to low magnetic fields spread out through this entire domain. Now, what's really great about what EOFSA has really brought to the table, at least one of the things that's brought to the table, I'm speaking from a theorist point of view now, is the ability to not only diagnose the energetic particle spectra, but also the magnetic field strength. And so if you look at this vertical current sheet in that data, they have done parallel MHD simulations of this, and they've matched the profile of the magnetic field along this current sheet with those MHD simulations. And the important thing from one perspective of comparing with our data is that they get the best agreement for a guide field of 0.3 times the reconnecting field. And I've told you how significant that guide field is. And so this is really a great, the ability to try to get a handle on what that guide field is really important. The other thing interesting to note here is that the nominal X line seems to be right around here, and it corresponds to a dip in the number of energetic electrons that they see in the data. This is the spectrum of electrons versus the height, the MEV along the horizontal. Okay, so we've been trying to then ask whether K-global results are in reasonable agreement with this great data. So for K global, if you have a guide field of 0.3 times the reconnecting field, we get a spectral index of 3.4. The ReSi photon spectral index was 4.4 in the coronal source. And for thin target Bremsstrahlung, that gives you a particle spectrum of 3.9. The OFSA spectral indices range from 2.7 to 5.6. So that's pretty good. We're getting 3.4 compared to 3.9 for ReSi and the same range for EOFSA. So that is good. What about the hot thermal temperature in the current sheet? An ODE EIS says that current sheet has a temperature of about 2.5 kilovolts. The K global estimate, which is 0.04 MCA squared, is about 0.6 KeV based on what our estimate for the alphane speed there is, which is about 1,200 kilometers per second. So look, this is not very good. We're off by a factor of 4. So we're trying to figure out whether we believe the K global estimate or not, and so that's still ongoing. The other thing I think is the energy content for non-thermal electrons. For this guide field, we predict non-thermals would really dominate strongly, and that's consistent with the general flare trends. And the rest is just conclusions, so I think I should stop here now, and then we'll have some time for questions.
Okay, thank you, Jim. So now we're open for questions and comment. I expect that Hugh wanted to make a comment first.
He did, yeah. Sorry to be first. But just, I couldn't help myself. When you were talking about the guide field dependence, I was thinking to myself, well, you know, it's pretty clear that in the impulsive phase of the flare, you're going to have very strong guide fields because the field is all twisted up and complicated. Then in the gradual phase of the flare, where you see this current sheet, you're going to have a very small guide field. So that's sort of opposite from what you're saying. I would, you could comment on that, but before you do, I'll just comment that one of the most striking things about hard X-ray observations of solar flares is this, what we call the soft, hard, soft variability. And so there's a test, right, of your guide field dependence. If you can show that the reconnection process anticipates that, then that would be very nice.
Okay, so let me comment about your soft, hard, soft is a very definite statement, and so I can try to answer that more clearly. In fact, we have thought about that. At the beginning phase of reconnection in a flare, it's going to be a very strong guide field, and the reason is because flares typically start with pretty wide current sheets, and as reconnection starts, it's not the asymptotic magnetic field that matters. It's the magnetic field just outside of the narrow current sheet that is the important magnetic field controlling everything. And at the beginning of the flare, then, the reconnecting magnetic field that's just right in that middle, in that region around where reconnection is taking place, will be extremely small. And that means that as the flare develops, the effective guide field goes down with time and then goes up to some, so you'll get some maximum value of the reconnecting magnetic field over the guide field. And then I don't know what happens at late time. But a model like this can certainly explain the soft to hard evolution of a flare. And whether it can explain the soft again, I don't know. We'll have to talk about that, I guess. But we know one of the things, you know, we've been collaborating with the Goddard group who are doing simulations of 3D macro systems. And, you know, I think the way to answer your question more thoroughly is to look at those simulations and then try to deduce from that what the actual, how the guide field versus the reconnecting field actually evolves as the flare evolves.
Okay, thanks.
Can I ask a question?
Yeah, go ahead, please.
Yeah, so Jim, what about why does K global give power law so easily? Is it just the physical size of the domain, or is it some physics that's missing in PIC?
No, the physics is not. PIC is not missing the physics, and of course, you know, we're in an ongoing discussion to try to understand that. But, you know, what I think is that the constraints on the size of the PIC simulation is severe, okay? Because we're trying to do 3D simulations, and it's difficult to separate the scales, both in terms of the proton to electron mass ratio, which is often only about 25, as well as the size of the total domain compared to the kinetic scales. And the problem is, imagine that the electrons start gaining energy, and you're looking at electrons which have a mass ratio of 1/25 of the protons. Once they start gaining energy, their Larmor radius starts getting big because you're not using real electron masses. And as soon as the Larmor radius of those energetic electrons approaches the scale size of the structures, they become demagnetized. And that demagnetization, I think, disrupts the energy gain process. So that's the feeling I have about the problem with the PIC. But of course, we are discussing this, and I don't think there's any final answers yet, but that's my best guess at this point. In K-Global, this is not an issue. Our electrons are guiding center, and the scale size of our structures are macroscopic. There is no kinetic scale structures anymore.
Okay, thank you.
Okay, other questions or comments?
Somebody had a comment at the very beginning, which I tried to, I was taken aback by. Can that person sort of comment now? Something to do with low flux.
Jim, some microphone was unmuted at that point. I don't think it was
Oh, okay.
relevant.
Okay.
But please go ahead if I'm wrong and ask question on my comments. Meanwhile, I want to make very brief comment toward Hugh comment. So in fact, in the same flare during main phase, we detected with the offset data a very strong decay of the magnetic field. So magnetic field in the cusp region decayed by a factor of 4 to 5. And this implies that the reconnecting magnetic field was same factor larger than the guide field, exactly where the energy release happens. Just brief comment. Okay, other questions or comments about Jim's talk?
Just wanted to make one comment.
Yeah, Dale, please go ahead.
Yeah. So Jim, when you were comparing with the 2017 September 10 event, and you gave some power law indexes, I guess next slide actually. So this range of spectral indices is not like an error bar, right? This is
No. I
totally measure it.
Okay, yeah.
Values.
No, I know that, but you should tell the audience that too.
Yeah. So I mean, we have very precise measurements of this at different places, and that's one of the things that can be very useful here when we compare exactly where this K-Global spectral index is happening. Because, one of the other groups we have is the transport group, and we have to figure out what happens to the particle indexes after they transport somewhere else.
Yeah, so you can, I mean, in some sense, this picture here I'm showing here makes your point, and that is, look at this wonderful data. It shows the spectrum of electrons as a function of energy and as a function of height. And so, and if you look at the Gary 2008 paper, they show the spectrum, and as Dale says, the error bar is not this. What I listed here was not an error bar. It's that there's a range of specific spectral indices at various different locations, and so this is a range of spectral indices AC as a function of different locations. That's what this is all about.
So this
Exactly,
slide,
thanks.
Jim, you show the you talk about the hot thermal temperature by the EIS.
Yeah.
Where was it taken? Do you know at what location? Is it in the current sheet?
Yeah,
I
the
thought
current sheet. This was the current sheet. If you look at the paper, well, I don't know. I suppose in some sense, no, this is not Hanodi data, but it's the current sheet. I think there was a broad peak. I think the statement in the paper is that there's a broad peak of the temperature along the current sheet. That's my
Okay.
memory of what they said. This is Harry Warren's paper.
Yeah, I think Django wants to ask question. Django, you are unmuted.
Oh, yes. This is Zhang Li in NGIT. In flare light curves composed of multiple peaks, does your simulation reproduce this feature like reconnection, start and stop, restart and stop, that repeating process?
So I'm not sure what you mean by peaks. One possibility is that reconnection started and stopped like you said, but the other possibility is that we do see bursty heating of electrons in all of these simulations. I mean, that goes back to PIC, and it's also seen in the K global simulations. But the burstiness is controlled by the formation, growth, and merger of islands, or flux ropes, if you want to call them, rather than reconnection really starting and stopping. So can you clarify what you mean by starting and stopping?
I mean, multiple peaks. You showed Stephen White figure, light curve, hard X-ray.
Oh, yeah, right.
These multiple peaks as one episode of reconnection, and that stops, and the restart and stops.
Okay, so here, is this what you're referring to? Say this
Yes,
here,
it is.
this here, this here, and this here.
Yes, it is.
Yeah. The K global as it exists now, we're not going to be able to explain this type of behavior. It seems like this is what our plan is. The plan is we have a collaboration going on, and our plan is to work with Goddard and their ARMS code. And the ARMS code is capable of doing realistic simulations in full flare geometry. And if we can add this type of physics into the ARMS code, then we can do a simulation in which the full geometry of the flare is included, including three-dimensional effects. And one might be able to then produce something like in this figure. Right now, we can't. I would say that what we're doing is exploring this single big peak here, and these multiple spikes may be associated with the merger of multiple islands in our simulation. But I'd say from here to here is the likely thing that we'd be able to model in our present simulations.
Okay, thank you.
Okay, do we have other questions or comments? I'm looking for... See, one microphone is unmuted, so do we have other question?
Can you hear me?
Yeah.
Oh, you can hear me?
Yes.
Okay, great. I just plugged in my microphone. So, Jim, this is Sheila.
Yeah.
Can we go back to the second last slide about the temperature?
Which part of the temperature?
So you say this is 4-time difference from the measurements.
Yeah, right.
And you may make sure you measure the temperature at the exhaust in the K global, right? From what you say.
We measured the temperature in the island structure.
In the island structure.
Yeah.
Which is not the exhaust, but the center of island.
Yeah, it's true that this is Yeah, it's true. Harry Warren's measurement was inside the current sheet. We didn't actually measure the temperature inside the current sheet, so we did. That's a good point, Chile. Yeah, maybe we should go back and check that.
So actually, especially in 2D, the central island is hotter than the exhaust. Is that right?
Well, depends on what you mean by the center. So, for example, if you go look at this data here, whoops. The one up above here is probably the measure of this is not the temperature, it's the energy, but nevertheless, the center of the island is actually rather cool, and you have a ring of very hot electrons, which were ejected from here now. So, whoops, I was hoping that I would go backwards, but it didn't work. Let me try to stop this at the right point. Oh, rats, it's not working. Anyhow, what I was going to try to say, Chile, is that if I stop this at some location, before I reach that final state, there might have been a hot distribution of electrons along there. Maybe we should have tried to measure that and then compare that. Because if you look at this movie a number of times, I think you'll see that there's some time duration in which there's some red stuff and before it gets injected in here, and that's clearly coming from the current sheet. And so, and maybe Harry Warren was measuring all this at some point at which there's a lot of hot electrons in here. I don't know.
And now you are measuring the the red part of it in Clay Gobel?
Right. So in the paper, Harry took a band of electrons around in this island here like this, and analyzed that band of electrons in terms of thermals and non-thermals.
Okay, I see. So it is indeed a difference.
I mean, look, it's these particles come from particles that were ejected from the current sheet into this thing here. So at some point, all these guys were ejected from the current sheet. I don't think all these particles were actually generated within this big island. I think they were generated in the current sheet through the interaction of multiple islands in here, and then ejected into this thing here.
Mhm. And by the way, what upstream temperature did you use? 100 EV in?
This one is this is higher than you might expect for flares.
Oh, I see.
But Harry has been checking that result to see if anything was sensitive to the upstream temperature. The conclusion from that is the spectral indices are not at all sensitive to what the upstream temperature is. And if you just look at the change in temperature of the hot thermal particles, then that temperature change is also not sensitive to what the upstream temperature is.
Okay, do we have any final questions or comments? Nothing. And so we are still working on the schedule for next Sulfur Colloquium talk. So right now the slots are open, but I will inform all of you about further scheduling. So next talk will be in 4 weeks from now. Thank you very much. Thank you, Jim. Thank you for participation.
Thank you for all the questions.